Actually, Kevin got it wrong. This is going to be a lecture about poetry. I couldn't resist putting up this. Well, actually, I had to suffer through this poem. Well, I shouldn't say anything about poetry. I really don't understand poetry. So, but it's the question of how the universe will end has intrigued people forever, and so it looks like actually we may actually have some idea how it's actually going to happen, and that's what I want to talk about today. So what I wanted to start out with is what we know. We know that the universe exploded about 14 billion years ago. Oh, I should say something. I was going to do some demos today, but in fact I couldn't figure out a way to blow up the universe, so we'll do some animations, but I won't actually do any demonstrations. We know that the universe exploded about 14 billion years ago in what's called the Big Bang. It's still exploding, or it's still expanding today. During the earliest times, the universe was very hot and dense, was filled with what's called a plasma, ionized gas. It was very hot and very nearly uniform. I'll talk about this a little bit more later. Now we know the universe is pretty cold. The average temperature of the universe is only about 3 degrees above absolute zero, and it's very lumpy. You look out there, you see bright spots, you see dark spots. It's not at all homogeneous, not at all uniform like it used to be. And so that's actually one of the things we want to understand is the development over the course of 14 billion years from this to that. And then what we'd like to do is, if we can understand that, we'd like to then extrapolate forward in the future and figure out what's going to happen, what's in store. So actually I realized the other day we're trying to predict the future by reading the stars, so in some way we're the modern day astrologers. For some reason people don't like to refer to themselves that way. But, all right, so what's my plan? The plan is I'm going to describe the expansion of the universe, and I'll show a few animations to explain what that means. It's my experience that there's a lot of confusion about what the expansion of the universe actually means. Talk about how we actually measure the expansion of the universe, and then how we can predict what's going to happen based on those measurements. I'll spend a tiny bit of time talking about non-Euclidean geometry. It turns out actually for cosmology as we know it now, we don't need it, but it might have been necessary. It happens that we don't, but I'll mention it briefly. And then I'll talk about two of the things that we actually measure to understand, that help us with our understanding of the history of the universe. One is the measurement of supernovas, and the other is the development of the structure, the evolution from the homogeneous, uniformly distributed material to the lumping, to the present-day lumpy universe. So, universe is expanding, and what does that mean? What that means is that if we sit here with our telescope, that's not a mega, this is my poor drawing here. Anyhow, that's a telescope. If you look at the stars or galaxies very far away, they're moving away from us, and the ones that are farther away are moving away from us faster. The speed is proportional to the distance. That's an important, and I'll show you the actual data. But before we get to the data, I just want to show you what this means. Just imagine a large sheet of rubbery graph paper. So this is the universe. Imagine the universe is just a sheet of graph paper, it's just 2 dimensions, and somebody's pulling on the corners. Or although actually this is an infinite sheet of paper, so the corners are actually not here, but some are way out here. But I've only drawn a little piece of the paper. So the paper is going to expand. And we are sitting here on this red galaxy, and there are some other galaxies here. Okay, so what's going to happen is, as the paper expands, the galaxies will move. And just to help, for reference, I've drawn these dotted circles around each of the galaxies. These dotted circles will not move. That's just to help, because it's a little disorienting when things start to move. So keep in mind that the dotted circles are stationary. Okay, so as the universe starts to expand, you can see what happens. See, here's this galaxy moving along. It started out in the middle of this circle. I'll back up. You can see that again. Okay? So the center of this circle doesn't move. But the galaxy that was here moved to here. The galaxy that was here moved to here. The galaxy that was here moved all the way over to there. So that's what happened. Okay? So here's the motion of three galaxies. The nearer one moved a certain distance. The one that was twice as far away moved twice as far. And so a uniform stretching of the rubber of this universe shows up in this, what I said, the speed at which objects are moving away from us increases with distance. The farther away they are, the faster they're moving. Okay, and this is what's known as the Hubble expansion. I'll show, it was discovered in 1929 by Edwin Hubble, and I'll show you his original data. It's actually interesting. But now, one thing I should point out is there's nothing special about this direction. Galaxies here will do the same thing. Galaxies over here will do the same. Galaxies here will do the same. And so it looks like we're at the middle, right? It looks like we're sort of, everything near us is not moving, and the farther away you go, the faster they're moving. It looks like we're the center of the universe. Okay? But let's look at it from the green galaxy's point of view. So what does Mr. Green see when he looks through his telescope at the galaxy? So I'll do exactly the same animation I did before. The only difference is I will focus in on what he sees, and so this point will remain stationary and these guys will move. So now as the universe expands, you can see now this is us. Remember, we're the red one. He sees us moving from here to here. The guy who was a little closer moved, but also not quite as far. And so he sees a similar sort of effect, and he thinks he's the center of the universe. Okay, there's no difference. So in fact, it looks, every person thinks he's at the middle, but there really is no center to this expansion. Every place in the universe is more or less the same. I mean, obviously there are lumps here and there are not lumps there, but on a big scale, on the big picture, every spot in the universe is the same, as far as we know. I mean, that's what it looks like. Okay, so that's the important feature of the expansion. Now, the question is, how do we know this is happening? Okay, the way we know is because of the Doppler shift, and I'll show a couple examples, but let me just show you the data first. So this is actually a photocopy of Edwin Hubble's original paper published in the National Academy magazine in 1929. And so here's some galaxies. Here's how fast they're moving away from us. They're moving pretty fast. See, these galaxies are moving 500 kilometers per second, and they are a megaparsec away. That's 3 million light years. A parsec is about 3 light years, so this is about 3 million light years. And the slope is what's called the Hubble parameter, how fast they're moving at a particular distance. So it's 500 kilometers per second at 1 megaparsec. So the ratio is 500, there's the constant, 500 kilometers per second per megaparsec. Okay? Now here's some new data, relatively new, from 2001, showing the same thing. All of Hubble, if you look here, this is 1 megaparsec, this is 200 megaparsecs. All of Mr. Hubble's data was right down in here. So this modern data goes out to much farther distances, and so you can see it's a reasonably nice straight line, and the slope is 70 kilometers per second per megaparsec. And you might wonder, gee, why did this number change so much? And the answer is, which I'll get to a little bit later, it's extremely difficult in astronomy to measure distances. So the problem was that his distance scale, this horizontal axis, was off by a factor of 8 or so. So there's nothing wrong with his straight line, it's the slope was wrong because the length of his ruler wasn't calibrated right. Okay? When you look out at a star, it's not so trivial to figure out, right, how far away the stars are. In fact, for a long time, right, the ancients thought they were just lights up in the sky, right? There's no way of knowing a priori that they're really billions or trillions of miles away. Okay, so that distances are very hard to measure. You can measure angles, you can measure brightness, you can measure color, But distance is not an easy thing to measure. Okay. So, I didn't want to do that. I want to do my demo. So, let's see if I can do the demo here. Right? The way we tell how fast objects are moving is with the Doppler shift. Right? You're all familiar with sirens, right? When the ambulance is coming towards you, the pitch is high, and when it goes by and is going away from you, the pitch is low. And this is my hokey demo of this, because I didn't want to go out, I didn't want to pull stuff from the web, because I didn't trust the web connection during a lecture. So this is my own homemade demo, which sounds terrible, but anyway. Right? So as soon as it goes away, when it's going away from us, the pitch goes down. Okay? And the same thing is true for light. What I'm going to show here is a demo. Imagine a star that's yellow like the sun, but it's coming at us very rapidly. Then the pitch, in this case the color, is going to be higher, which means blue. So imagine a star coming at us very rapidly. It slows down. When it stops, it's going to be yellow. So it's going to come in, it's going to look blue. Stops, it's going to be yellow. And then as it accelerates away, it's going to be red again. So, or redder, it's going to go back. It's going to become red as it goes away. Let's see if that works. All right, so there we are. When it's coming at us, it looks blue. When it stops, it becomes yellow. And as it accelerates away from us, it gets redder and redder. And that's how we can tell that these galaxies are moving away from us, is because they look redder than they ought to. It's called the redshift. And we measure that. We can measure. So this is the vertical axis on these plots is reasonably straightforward to measure. We just measure the color of the objects, and we compare with what they ought to be. Okay. So if I can get PowerPoint, there we go. So why is this expansion rate important? Okay, the first thing I want to mention is the animations with the rubber sheet that I showed showed a constant expansion, mostly because that's the easiest thing for me to animate. But right. But in fact, that's not what we expect, right? If we expect the expansion to slow down with time, just because of the mutual gravitational attraction. We have a bunch of stuff moving apart. They're all exerting gravitational forces on each other, and you expect it to slow down. Just like if you throw a rock up in the air, the Earth is pulling on the rock, and the speed will slow down. Right? So that's what we expect to happen. We expect the expansion of the universe. That star is fading out. Let's try a different one. All right. We expect the expansion of the universe to slow down due to the mutual gravitational attraction of all the stuff in the universe. Okay? Like stars, black holes, gas, whatever it is. Gravitational attraction will cause things to slow down. Okay? And so in the case of the ball, it'll slow down and fall back to the ground, unless the speed exceeds the escape velocity. And so the natural question for the universe is, does the expansion rate exceed the escape velocity? Because the fate of the universe hinges on the answer to this question. All right, so here are two plausible scenarios. Right, here we are now. Imagine that sheet of paper again. At a particular time, namely now, that paper has a certain size, and it's expanding at a certain rate. Okay, so that's the slope of this line. The size of the universe it's expanding at a certain rate, and that's what we can measure. That's this Hubble parameter, 70 kilometers per second per megaparsec. Okay, in the past, it was expanding faster, right? It was expanding faster, and it slowed down because of the gravitational attraction. And so the question is it going to expand forever? If the expansion rate, if it's faster than the escape velocity, it's going to expand forever. And you know that things as they expand cool off. And so that's the ice scenario. If the universe expands forever, it becomes less and less dense and colder, and we end up with basically an icy, dead universe. Of course, if the expansion is less than the escape velocity, then it's going to reach some height, some maximum size, and it'll stop, and then it'll come back together and collapse in what's known as the Big Crunch. And when it comes back and collapses, as things get compressed, they get hot again. And so that's the fire scenario. In the fire scenario, the expansion universe stops, and it collapses back to a recreation of the Big Bang. It was very hot here in the early universe. In this scenario, it'll be very hot here again as things collapse back. Right? So those are the alternatives. And the question is, how do we make that decision? The way we predict the future is by measuring the past. We want to measure the shapes of these curves, and then by extrapolating these curves into the future, well, one or the other, we don't have both. The question is, which of these curves is right? So by making a measurement of this, we can then extrapolate into the future and determine what the fate of the universe is. Okay, that's the plan. Or at least that was the plan 10 years ago, and people did these measurements. Okay, now, what would we like to do? Let me back up and just remind you. What this is a plot of the size of the universe as a function of time. So that's what we would like to measure. Okay, we'd like to measure the size versus time. The problem is that's not possible. We can't make those measurements directly. What we can measure is expansion rate versus distance. We can't measure time directly. We can only measure, and even distances are difficult. Time is impossible. You can't look out there and know what time the light left that star, not without doing some calculations. Okay? So, but if we can measure expansion rate versus distance, then we can use the fact that distance is rate times time, and we can convert it to the plot we want. Okay? This calculation, unfortunately, involves calculus because the rate isn't constant. These things are curves, and you have to use a little bit of calculus, so I'm not going to go through it. But that's the general idea. Okay? So, the way we measure distances is with supernovas. All right, so I'm going to show you an animation. This is a beautiful animation done by some collaborators at Berkeley. This is 3 different views of a supernova. So here's a galaxy, and there's going to be a supernova right here. And what's going to happen is I'm going to do an animation. You'll see the supernova get bright and then dimmer. So it's a whole bunch of photographs taken over. This is a several-month period. It takes, when supernova explodes, it takes about 2 weeks to reach its maximum brightness, and then it fades away over several months. Okay, and so the movie will show that. The supernova will get bright and then dim, and this plot is just a plot of the intensity. And at the same time, I'll show you the colors. And one of the things about the colors is you'll see that there are features. There are dips in the spectrum, and the color, where those dips occur, tell us how fast the star is moving away from us. Or that's the blue. That's how we measure the redshift of the supernova, is by measuring the color at which those features. You can even see the features now at the very beginning of the movie. All right, so that's what I'm going to do. Is I'm going to play the movie. I hope. There we go. All right. Let's see if I can back up and play it again. All right. You saw the star get bright and then dim. That was what this plot shows. And you can see the colors appear. Right? And you notice there are the features there with the dips. Those are absorption. They're the various chemical elements in the star's atmosphere absorb particular colors of light. And in particular, there's a lot of nickel in these supernovas. And if you can measure the spectrum of nickel in the laboratory and compare that spectrum with what you see in the star, and by measuring the shift in colors, that tells you how fast the star is moving. Okay, so those are the 2 important things we measure here, are the brightness of the star and its redshift. Okay? And let's see how does that help us. Let me get rid of this. Okay, the brightness tells us the distance. This is one of the big discoveries in the last 20 years, is that we can use these supernovas to measure distance. This is a big advance. As I said, distance is not an easy thing to measure in astronomy. The way we measure the distance is by using the inverse square law. Right? If we know how bright an object is, then we know as the light, here's the star, as the light goes away from the object, its intensity drops as the square. Just because the surface area of a sphere is proportional to the square of the distance of the radius, as the light has to spread itself out over the whole surface area of the sphere, so the brightness at any one spot goes down inversely with the square of the distance. Okay, so if we look at that star, if we know the intrinsic luminosity of the star, that is the total amount of light that it emits, and then we measure its apparent luminosity, that's the amount of light that enters our telescope. So you can see our telescope has a certain amount of area determined by the size of the mirror. The farther away that star is, the smaller fraction of the light enters the telescope. So we can get the distance by comparing how much we actually detect compared to its intrinsic luminosity. So this is the important feature, is that there's a certain kind of supernova for which we know the intrinsic luminosity. That was the big discovery, was that there's a type, what's called type 1a supernovas, which I won't talk about. There are different kinds of supernovas. There's a particular kind. Fortunately, it's the most common kind. So they're not rare. They're not rare supernovae. Well, all supernovas are rare, but they're not any rarer than that. You only get about one supernova per century per galaxy. So if you want to see a lot of supernovas, you have to look at a lot of galaxies. But all right. So these supernovas are what are called standard candles. They're all the same to within 10 or 20%. That's actually one of the big research issues, is how accurate is, how good are they as standard candles. But they're good, certainly good to 10 or 20%. Okay? Now, one thing you might worry about is, this is my slight digression into non-Euclidean geometry. You might worry about the fact that you've heard that in general relativity we have non-Euclidean geometry. Space is curved and not flat. And that might screw things up. The problem is that if the geometry is not flat, suppose we have a spherical geometry. So here's a sphere, and I draw a circle of some radius r. If I calculate the circumference of this circle, it's smaller than 2 pi r. On a saddle type of geometry, I draw the circle of radius r. The circumference is bigger than 2 pi r. And if the light spreads itself out uniformly, the light's leaving the star isotropically, then what's going to happen is, in the spherical universe, the star will be brighter than you expect. And in the saddle geometry, the star will be dimmer than you expect. Dimmer because it has to spread itself out over more circumference. This works in 3 dimensions too, but I can't draw 3-dimensional non-Euclidean geometry. That's a pretty hard graphics problem. So, fortunately, we're in luck, because as far as we can tell, the universe is flat. So this is a worry that one might have, but in fact, it turns out not to be a worry for cosmology. As far as our measurements of the geometry of the universe indicate that the universe actually is flat geometry, and so I don't need to worry about this. But I wanted to mention it because it's something to worry about. Okay, so anyhow, as I say, non-Euclidean geometry is interesting. It's interesting when you talk about black holes and all kinds of other stuff where non-Euclidean geometry is important, but that's a different talk. Is that on the agenda? Not this fall. All right. Anyhow, just think about it this way. Think of a golf ball. It's approximately spherical, but it's got little bumps on it. Right? So if I want to look at small scales, imagine each of these little bumps is a black hole and it causes curvature. But on a big scale, on the scale of the whole ball, it's more or less smooth. Or the same thing with the Earth, right? If you look at the Earth from space, it looks pretty smooth. But if you look up close, it's got bumps. So on the large scale, which is what we're interested in for cosmology, it's all smooth. It's all flat, and we don't need to worry about the non-Euclidean geometry. Okay, so they did this measurement with the supernova, and this is what they got. This is a result that was first done about 10 years ago by groups at Berkeley and at Harvard. Two different measurements done almost simultaneously. They were surprised to find the result. The result is that neither of the two curves that I drew is correct. Okay, what they found was that way back early in the universe, in fact, the expansion universe was slowing down as expected. But in recent times, it's actually not slowing down at all. It's accelerating. It's curving upwards. Like that. Okay? That's pretty weird. Because remember, I argued that it should be slowing down due to the gravitational attraction of all the stuff in the universe. So the fact that it's speeding up is an indication that something weird is going on. Right? It's as if, suppose you threw a ball up in the air. Suppose you threw a rock or a ball up in the air, and instead of slowing down and falling back down, it accelerated. Right? That's what's happening here. That's pretty weird. Right? So if you saw that a phenomenon, what might you conclude? Well, I can think of two obvious, you can probably think of others, but the two obvious conclusions would be, one, that there's some weird anti-gravity material that's actually pushing the rock up in the air. I mean, if you look up there, there's not like another planet up there pulling it up. Right? We can see that there's nothing up there pulling. So, but you could imagine that, well, gee, maybe there's some weird anti-gravity stuff in the Earth and it's pushing that rock up. Maybe. That's pretty strange. The other is that maybe our theory of gravity is wrong. Right? I mean, it's worked so far, but you know, just because theories work for a while doesn't mean that they're guaranteed to be correct. There have been lots of theories that have worked for hundreds of years, which have then been shown to be wrong. Not wrong is not the right word. Not applicable in certain situations. Okay, you have a theory that works and describes lots of phenomena, then you extend it to describe new phenomena. Maybe that extension works, but very often or sometimes the extension to new phenomena fails, and you have to modify the theory. And that happens. That's not an unusual occurrence, and maybe it's happening now. We certainly have to consider that maybe Einstein's theory of gravity is not correct. That's a possibility, which I'm not going to consider. Okay? So I will assume that the theory is right. In fact, people are looking for violations of general relativity, and so far they haven't seen any. So there's no obvious evidence that the theory of gravity is wrong, so I will assume that it's right for the purposes of this talk. Okay? So if the theory of gravity is right, then the universe must contain enough of this weird material, which people have called dark energy. When people talk about dark energy, that's what they're talking about. They're talking about the stuff that's responsible for this acceleration of the expansion. Some kind of anti-gravity material, which is enough of it to overcome the gravitational attraction that the regular stuff has. Okay? And by looking in detail at the shape of that curve that I showed, we can infer that this dark energy constitutes about 70%. It's not like it's an unusual stuff. It's more than 2/3 of all the stuff in the universe is this weird anti-gravity material. Right? It's just not easy to see because it doesn't make atoms and whatever. Can't make iPods out of it. All right. Now, there's another actually interesting feature, which is a little more subtle. We have to think about it. I'll go through it a little more slowly. The fact that the expansion was once slowing way back in the early universe and is now accelerating indicates another interesting feature of this dark energy. That means that when the universe was small, the density of matter was large, right? As you work your way back in time, the universe gets small, the density of the matter gets large, the gravitational attraction of the matter is much stronger. In fact, and the curve is decelerating. But that means that when you work, if you run the movie backwards to a small universe, the density of the matter is increasing more rapidly than the density of this dark energy, because in the early universe, the matter was overwhelming the dark energy and causing the expansion to slow. But as the expansion proceeded, the density of matter decreased, just 1 over the volume, right? The density is 1 over the volume. As the volume increases, the density of matter goes down, but the density of the dark energy does not go down. And so therefore, at late times, the dark energy dominates, because the normal matter decreases in density, but the dark energy doesn't. So the density of the dark energy does not decrease as rapidly as that of the matter. That's implied by the fact that the curve was going this way and is now going this way. Okay? In fact, the evidence so far, it's not a very accurate measurement yet, but the evidence so far is that the density of dark energy doesn't go down at all. It's very possible the density of the dark energy is a constant, which is pretty strange. What kind of material density doesn't decrease as you expand the box that it's in? But that's the evidence. Okay, so this is strange stuff. That's one reason why you might think that gravity is wrong. Right? This is a pretty weird conclusion if we accept the theory of gravity. So that's why people are seriously considering the possibility that maybe the whole theory is just wrong. Okay? Now, I want to talk about another weird feature of the universe, which is important actually, which is the dark matter. The dark energy is not the only weird stuff in the universe. We also, it turns out, oops, I had made some modifications to this slide. Anyhow, nothing real important, but it didn't show up. It turns out the matter we see all around us, the atoms that make up the normal material, is only about 4% of the total. It's 15% of all the matter. See, we have 70% is dark energy. The other 30% is matter of one form or another. But of that remaining 30%, only 15% is the normal kind of matter that we see. Atoms. And this kind of stuff. Okay? So when I say 15%, I mean 15% of the remaining 30%. That was the part I edited because I thought it was a little confusing. The rest of the matter, the remaining 26%, is what's called dark matter. By dark, I mean it doesn't emit light. When you look out with your telescopes and you look at the galaxies and stuff, you're seeing the light emitted by the atoms in the galaxies. It turns out there's about 7 times as much matter out there which doesn't emit light, whose existence we can only infer because of the gravity. If you look at the orbits of stars around galaxies, for example, the stars are orbiting too rapidly, because there's more gravitational attraction in the middle of the galaxy than you would expect. Okay, so we infer the existence of the dark matter from its gravitational properties. There are several pieces of evidence for dark matter. I only want to talk about one of them because it's important in the cosmology. Okay, so let me look at the universe when it was very young and hot. Remember, way back almost 14 billion years ago, the universe was very dense and very hot. Here's a map of the universe. If the Earth could exist then, suppose there were an astronomer and he looks out with his telescope, what would he see? This is what he would see. This is a sky map of the universe made by an astronomer 400,000 years after the Big Bang. It's basically more or less uniform dull red color. There are no stars, no galaxies, perfectly uniform, glowing a dull red color. It's glowing a dull red because it's about 3,000 degrees, which is a little bit cooler than the sun. The sun is yellow. This is a little cooler than that, so it's only red, like the hot burner on your stove. Okay? That's it. The universe is, basically what it is because before there were any stars and stuff, the universe was just full of hot gas. and are pretty much uniformly distributed. Okay? But not exactly uniform, and that's an important point. If I take this picture and I enhance the contrast by a factor of 100,000, I get a map that looks more like this. The colors are different. This is just a color coding where the red is the high density regions and the blue are the low density regions. But this is, as I say, I've enhanced the contrast by a factor of 100,000 so that the bright regions are 1 part in 100,000 more dense and the dark regions are 1 part in 100,000 less dense. Now, to give you an idea of how smooth this really means, imagine the Earth. The Earth is a radius of, say, 4,000 miles. 1 part in 100,000 is 200 feet. So if the Earth were perfectly smooth and the highest hill on the Earth was 200 feet, that's how smooth the universe was 400,000 years ago. Right? Smoother than any billiard ball that you can make. Right? Nice and smooth, that's not smooth enough. These tiny fluctuations are actually important in the history of the universe because a dense region has more gravity than a less dense region. Right? A little more density means a little more mass, so it's going to start attracting material into the dense region. So what happens is the rich get richer and the poor get poorer. Basically, you have mountains and you have valleys. The mountains get taller, the valleys get shot deeper, and this distribution, the contrast gets stronger and stronger. And so what happens is you have growth of structure as the universe evolves. And so if we simulate that, given the theory of gravity, we can simulate how the structure grows. So here you start out with an initial condition almost uniform. We have to specify the initial conditions. I won't talk about how that's measured. We can actually measure those initial conditions. But here, look, see, here's a tiny region here's a region that's a little more dense. As we evolve in time, you can see it's getting a little more dense. Things begin to clump together. Then it gets more dense and more, and eventually we have blobs. Now, we have to be careful. This is the big picture. These blobs are not stars. They're not even galaxies. These are clusters of galaxies. This is what I call the big picture of the universe. I'm talking about large-scale structure. Okay? But the same thing happens on smaller scales. It's just that our computers aren't powerful enough to do the simulations. So you have to stick with the big scales just to keep the computations something you can do in a reasonable amount of time on a supercomputer. Okay. Now, one thing I should be careful about, this doesn't show the expansion of the universe. As time progresses, this cube ought to be getting bigger and bigger. But just to make the graphics easier, I didn't show that part of the expansion. So this cube is actually expanding as at the same time that the gases get clumping together, the whole thing is expanding. Okay, now the question is, how rapidly do these structures form? That depends on how much gravity there is, right? The rate at which stuff falls into the holes depends on how deep the holes are. Well, it turns out that the structure formed, if the only matter there is what we see when we look through our telescopes, the stars, the stuff that emits light, the structures don't form as rapidly as we actually observe them forming. That was actually a big mystery for a long time, is why is it that the stars formed so early in the universe? The first stars formed approximately 1 billion years after the Big Bang, and that was hard to understand given that if the only matter there was the normal matter. This is just a graph of how we expect the perturbations to grow, how rapidly the heights of those hills on the billiard ball grow. If there's only matter, the height grows linearly with time. Okay? But we need to have more matter because we know that the stars formed earlier than would have been predicted. So you have to make this slope steeper. That makes the star certain. You need a certain amount of structure in order to have stars, and that was the one piece of evidence for the dark matter was the need to have more gravity in order to form the structures earlier. But we know how much structure there is now, because you just look out there, you can see how much structure there is, how many galaxies there are in a certain volume of space. So we needed for the structure to start forming very rapidly and then to slow down. And the dark energy is what makes the formation of the structure slow down, because the dark energy makes things remember, it's causing the expansion to accelerate. So the dark energy makes things be farther apart than you expect because it's accelerating, right? Therefore, because they're farther apart, the gravitational interactions are weaker, because the gravitational force falls off as 1 over r squared. Therefore, because they're farther apart, it's harder for the structures to form. The gravitational attraction is weaker. So initially you have a rapid form of structure because there's dark matter, and then later on you have a suppression of the structure because the dark energy makes stuff be farther apart than you would otherwise have. Okay? So that's the current picture of the universe. All right? And I just drew these things again. Remember, the billiard ball, the lumps on the golf ball are growing with time, same way as the lumps, well, anyhow, right? Things were very smooth, but they're now getting to be very lumpy. So that's where we are now. Antigravity has never been observed before, so that's something really weird. There's no good theory of it. So that's one of the big research topics nowadays in astrophysics, is to try to make better measurements of the properties of the dark energy so that we can try to develop a theory of what it actually is. There is a theory of the dark matter. In particle physicists, one of the goals of the new accelerator they're building in Geneva in Switzerland at CERN, which some people like Kevin are involved with, is to search for the particles which might be the dark matter. Okay, so there's actually a very deep connection between particle physics, as Kevin mentioned, the study of the very smallest objects, and the study of the history of the universe, is that the dark matter might be made of a new kind of particle which has been theorized but not yet seen. So that the dark matter makes up about 25% of the universe, and the remaining 4 or 5% is the stuff that we all know and love. All right, so that's pretty humbling to think that all the stuff we worry about in our everyday lives is really only 4% of the universe. The study of dark energy has become a major research area, which that's what I work on now, having abandoned particle physics. But as I say, there's a very tight connection between particle physics and cosmology. And one of the things I had added but didn't make it to this version of the PowerPoint is that as far as we can tell, the fate of the universe is the ice scenario. Right? If this accelerated expansion goes on forever, there is not going to be a collapse. However, we don't really understand enough about the properties of this dark energy for me really to make a definitive statement. But that's the way it's looking now. But you know, maybe 5 years from now things will be different, because we really don't know enough to really make a definitive answer to that. And I think that's the end of the talk, except for this wonderful slide, which I only put up because one of the nice things about astronomy is that it makes pretty pictures. And the other thing is, there's a supernova in this picture. And I will give a free cinnamon donut to the person who can figure out which one is the supernova.